All right. Hello, everybody. Like I said, thanks for joining me here today. Different scenery. I'm traveling right now, so bear with me. But today we're going to be talking about loading and performance. For those of you who are new, my name is Taylor. I am a certified flight instructor. So my full-time job, I teach people how to fly fixed-wing aircraft. I joined Altitude University back in September to help with the Part 107 part of the program because these are topics that I teach my flight students pretty much every day. So I've had a lot of fun being part of Altitude University, taking over these live Q&As. I did open up the chat, so you guys should be able to throw some messages in there and throughout today's session. If you do have any questions, there is a designated Q&A area. So for questions, throw them in there. I'll get to those at the end, whether it's on today's topic or any others from the course. Other than that, feel free to throw some messages in the chat, especially when we are going through the questions at the end. So like I said, my name is Taylor. Oops. We're going to go through today's topic, and then we'll go through questions that you might see on your written test at the end, and then I'll open it up to open Q&A. So to start off, operating with a payload. Well, what is a payload? Well, it's a term that we use when we're talking about weight and balance. So with weight and balance, first we have our empty weight. Now, these are terms that are typically used in general aviation for manned aircraft, but working or operating with a payload definitely affects us as Part 107 pilots. But just so that it makes sense, I'm going to give you guys a few other definitions that also kind of tie into that. So we have our basic empty weight, which refers to an aircraft's weight to include unusable fuel and oil before you're adding passengers and usable fuel. Then we have our useful load, and our useful load is now the amount of weight we have available to add fuel, passengers, cargo, and all that fun stuff, given the limitations of the aircraft. Now, the payload is basically the useful load just without the usable fuel. So what we're concerned about here with the payload is the weight of occupants, cargo, and baggage. Now, the FAA doesn't require that we as Part 107 pilots are documenting the payload for each flight. However, it's highly recommended. Now, anything by the FAA that's highly recommended, I definitely encourage you guys to do, even if that means it takes you a couple extra minutes before your flight. But in the event that something goes wrong and there is an emergency or an accident, the FAA might want to see your flight loads to make sure that you are operating within the limitations of the aircraft. Also noted is that operations involving hazardous material is strictly prohibited by the FAA. Now, you can find a full list of dangerous goods on the FAA website, but some examples are going to be things like cooking sprays, things that are flammable, maybe some sort of cleaners. Those are going to fall under that list of hazardous material. Now, weight and balance. Weight and balance is so important to compute. You will find in the manual for your drone how to compute the weight and balance. At the end of the day, the basics of weight and balance is the same, but every manufacturer might have a different way of calculating it. So definitely look in your manual for your drone to help you calculate that. But it's important that we are calculating these before our flight, because if we're operating outside the limitations of our aircraft, that's when we can be in a dangerous flight. So I'm going to make sure that we are doing that ahead of time. Again, check your manual. There should be a lot of detail from the manufacturer on how to compute that. Some terminology that we need to know about weight and balance, one being POH, which is the Pilot's Operating Handbook. That's where you're going to find the information regarding limitations of your aircraft, as well as how to compute the weight and balance. Then we have these two terms, forward center of gravity and aft CG. Now, before I get into that, I'm going to talk a little bit about stalls, because the characteristics of both this forward center of gravity and FCG has to do partially with how our aircraft stalls. So when we are talking about the four forces of flight, which we'll actually get into the next couple of slides, one of them is lift. Now, in order for our aircraft to generate lift, we're dependent on the laminar airflow over an airfoil, or the smooth air that flows over an airfoil. Now, I have just this graph up here. Let me move me to the side so I can show you guys. So over here we have a wing. And what this is depicting is the air and what it's doing when a wing stalls. So a few other terms that we need to know is one of them is the angle of attack. Now, the angle of attack is defined as the angle between our chord line, that chord line being an imaginary line from the leading edge of our wing, which would be the front here, to the trailing edge of our wing. So if you imagine an imaginary line here from the leading edge to the trailing edge. Then we have relative wind. Relative wind acts opposite and parallel of our flight path. So say that our aircraft here is flying to the left of the screen. Our relative wind is going to act opposite and parallel to that airfoil. So that relative wind is going to be moving to the right of the screen. So the angle between this chord line here and the relative wind is called our angle of attack. Now, this becomes important because every aircraft or airfoil has what's called a critical angle of attack. So as you can see, we have low angle here, a medium angle, and then an excessive angle of attack. Now, in these two top ones here, we still have that smooth laminar airflow over that airfoil, and that's what we're dependent on to generate lift. Now, if you exceed what's called the critical angle of attack, you can see now that laminar airflow got disrupted and it's no longer smooth. So we are developing lift still, but not enough to keep the aircraft suspended in flight. So most of the time that critical angle of attack is between 16 and 18 degrees. It's not important to know the exact degree because it's going to be different per aircraft, but it's somewhere within that range. So all that needs to occur for a stall to happen is that you exceed that critical angle of attack. So now that I've got those definitions out of the way, back to the terminology for weight and balance. So we have forward center of gravity, or CG, you'll see that as CG most of the time, or aft CG. So say we have our drone, right? We have our aircraft, and we have our center of gravity in the middle. And then you have a range for that center of gravity that our aircraft needs to be loaded within for it to be able to sustain flight. Now, if you had that range and you had forward center of gravity, so towards the forward end of the aircraft, all the way at the end of that little range here, the characteristics associated with that is that we're going to have a higher stall speed, a slower cruise speed. However, we're going to be more stable. Now, on the opposite end of that is the aft CG. So if we had that range again, in the POH, if you're looking in the weight and balance, they call it an envelope. So that's our range for our center of gravity. Now, if you're on the opposite end of it, you're on the aft CG, so the tail end of it, we're going to have a lower stall speed. We're going to have a faster cruise speed, which is great. However, we are less stable altogether. So at the end of the day, personally, I would give up some speed so that I could be more stable. This becomes really important when we start talking about stalling aircraft. All right. Then we have our forces acting on an aircraft. So we just talked about lift. That's our force up here on the top. We have thrust, which is going to be that force pulling our aircraft forward. Gravity is our weight, and that's opposing lift. And then we have drag, which is opposing thrust. So the FAA definition of each of these terms, thrust, it's that forward force produced by the propeller or rotor. Or in other words, it's propulsion system that moves an aircraft forward. Drag is that opposing force acting as a resistance to the forward motion of our aircraft while it's in flight. Lift is our force that directly opposes the weight of an airplane and holds the airplane in air or aircraft. And then weight is the force of gravity. Now, all of these terms are going to be things that you do see on your written test. Then we can talk about the stability of our aircraft. So the stability of our aircraft can be measured by its ability to correct for conditions that might disturb its equilibrium and to return or to continue on the original flight path. So what that means is if we're flying our aircraft straight and level, and say a gust were to cause our aircraft to now be pitched up and now we're climbing. The measurement of the stability of our aircraft is its ability to return back to that straight and level flight. One of the main ways that stability is kind of incorporated is the manufacturers and the engineers who are developing our aircraft, they have stability in mind. So most of our stability is going to come from just the basic design of our aircraft. Then some sub-terms within stability is maneuverability and controllability. So maneuverability is the quality of an aircraft that allows it to be maneuvered easily and to withstand stress imposed by maneuvers. Now, we'll see the next couple slides what I mean by stress imposed by these maneuvers when we talk about the bank angle. But some of the things that this is governed by is aircraft weight, inertia, size and location of our flight controls, overall structural strength of our aircraft, as well as the power plant. Then we have controllability. Now, this is going to be the aircraft's response to our input, us being the pilot. So how the aircraft is responding to our inputs while maneuvering the aircraft, regardless of its stability. Then we get into load factors, and this is measured in Gs. So the design of an aircraft is made to withstand a certain amount of overload. And this is really important to note about the limitations on your aircraft and to be really familiar with these numbers, because we can withstand a certain amount of Gs, but as soon as you exceed that, that's when you get into unsafe flight, and you can have an accident, somebody gets hurt, things like that. So understanding the limitations of our aircraft is really important. We want to be preventing stalls or any unsafe characteristics of flight. So some notes before we get into the graphs. One, the maximum load factor at a given bank angle. Now, when I'm talking about bank angle, we're talking about basically in layman's terms, when we're turning an aircraft as opposed to straight and level flight, we're measuring that turn in an angle. So that's called our bank angle. It is a proportion between lift and weight. So the maximum amount of excess load we can withstand on our aircraft is proportional between lift and weight. And we'll take a look at that in the next couple slides at the graphs. Now, like I said earlier, what's so important to remember is that stalls happen when your aircraft exceeds the critical angle of attack. That is all that needs to occur in order for you to stall. I don't care how fast you're going. I don't care how heavy you are. All that needs to occur is that you're exceeding that critical angle of attack. Now, when we were talking about weight and balance earlier, there are some characteristics that can affect the speed at which you're stalling. However, at the end of the day, the only thing that's occurring is that you're exceeding that critical angle of attack. I know for sure that is a written test question. So definitely reiterating that. Here we have a graph which shows on the left-hand side here, our lift coefficient is going to be this blue line here, and our drag coefficient is going to be the red line. Now, we have our angle of attack down here at the bottom. And like I was saying earlier, the typical critical angle of attack is between 16 and 18 degrees. So we can see that our lift coefficient is increasing throughout the graph until we get right between 15 and 20 degrees. And then you can see that lift coefficient drops dramatically, while our drag coefficient is increasing exponentially. So this is just showing where our aircraft stalls. Then we have our load factor chart. So down here, we have our bank angle in degrees, like I was talking about earlier, and the associated load factor. So, oops, let me go back one really quick. You can see right about the 45-degree mark here, that load factor increases exponentially. And that's really important to note when we go through the next few slides. So our load factor over here, like I said, is measured in Gs, which I'm sure is a term that you guys are all familiar with, especially if you're an aviation enthusiast. And the way that you read this chart, I'll go through this example. If an airplane weighs 23 pounds, what approximate weight would the airplane structure be required to support during a 60-degree bank turn while maintaining altitude? Now, both of these graphs you guys are going to have access to while you are taking your written test. If it is a load factor question that you have to do a calculation on, they'll refer you to the figure for this. But you can either be given it in numbers or you'll be given this graph here. So we're talking about a 60-degree banked turn. So at 60 degrees, you're pulling 2 Gs. So now an aircraft that weighs 23 pounds feels like it weighs 2 times that. So our answer here would be 46. Our answer is C. So you just take the weight of the aircraft, multiply it by the load factor, and that's how much weight the aircraft now feels like it is. If you're banking an aircraft greater than 72 degrees in a steep turn, which is a maneuver that we do in flight training, if we were to go back on the graph, you would see that it produces a load factor of 3. Now, our stall speed also increases significantly, and the turn is made in an aircraft with a normal unaccelerated stalling speed of 45 knots. So in the aircraft that I fly, our stall speed is 45 knots. That's a normal unaccelerated flight. But our stall speed increases in proportion to the square root of load factor, which is this equation here. So going back to that example, if we're banking an aircraft greater than 72 degrees in a steep turn, producing a load factor of 3, that stall speed's also increasing, and the turn is made in aircraft, like I said, that normally has a stall speed of 45 knots. Then our airspeed must be kept greater than 75 knots in order to prevent inducing a stall, because we've increased that bank angle by so much. One of our first questions here, question number 1, at what bank angle does the load factor of the aircraft start to significantly change? Either A, 15 degrees, B, 30 degrees, or C, 45. This is where I'll have you guys put your answer in the chat there. I'll give you guys a second to answer, and then I will answer it with you. So you can either look at the chart here and follow the line, or, well, it's kind of obvious on this chart, a little bit more obvious than the numbers here. Awesome. Thank you guys for putting in your answers. Our answer is cool. Our answer is C. So it starts to significantly change at 45 degrees. Again, you can see that here in the chart, relatively low up until 40. And then at 45, that's when we see that exponential change in our load. When loading equipment on our small UAS, you should attach the items in a way that A, does not adversely affect the center of gravity, B, is visible to local law enforcement, or C, can be easily removed. Again, going back to when we're talking about weight and balance and loading our aircraft, forward, aft CG, all of that fun stuff. Woohoo, lots of participation today. Thanks, guys. All right, our answer is A, does not adversely affect that center of gravity. Again, I highly encourage logging the weight and balance for every flight, especially if something were to go wrong in flight, you have proof that you loaded your aircraft appropriately. Which of the following is correct regarding the weight and balance of a small UAS? Loading and performance standards are always established by the manufacturer for all small UAS operations. Operations outside weight and balance limitations may result in a loss of control, or you can operate an aircraft above 55 pounds if the aircraft has a final landing weight below 55 pounds. All right. Yep. Our answer here is B. Operations outside weight and balance limitations may result in a loss of control, just like we were talking about in the first couple of slides. A stall occurs when the smooth airflow over an aircraft's propeller is disrupted and the lift reduces rapidly. This can be caused when the propeller either A, exceeds 1G, B, exceeds a critical angle of attack, or C, exceeds a maximum operating weight. Woohoo, you guys are on a great streak here. Yep, our answer is B, exceeds the critical angle of attack. All right, maximum endurance is obtained, we didn't really talk about this too much, at the point of minimum power when the aircraft's either A, at slowest speed possible, B, in long distance endurance mode, or C, in steady level flight. If you guys have already taken our course, you might have seen this question already. Our answer is C. So the maximum endurance, is obtained at the point of minimum power when we are in steady level flight. What is the best source for a small UAS performance limitation? Either the AIM Aeronautical Information Manual, B, DJI Go app, or the manufacturer's publication. Awesome. Yep, our answer here is C. I would like to say, though, the AIM is a great resource, not for small UAS performance limitation, but it's part of our FAR AIM, the FARs being the FAA regulations. And then the AIM is the second half of that book. If you guys ever get a paper copy of it, has great information regarding airspace. Not all of the information in the AIM is going to pertain to unmanned aircraft, but there's quite a bit back there, especially by reading airspace and the rules associated with it. It basically takes the regulations, especially the ones that are a little bit harder to understand, and explains it a little bit better. It gives suggestion on procedures and really good graphs. So I definitely recommend using it as a resource while you guys are studying, or even as you're actively flying. As a Part 107 pilot, if you have questions, while you are flying, it's definitely a great resource. All right, back to our load factor chart. If a small UAS weighs 20 pounds, what approximate weight would that small UAS structure be required to support during a 70-degree bank turn while maintaining altitude? It's either 20, 40, or 60 pounds. You guys are killing it with the answers. Our answer here is C, 60 pounds. So you could do it one of two ways. You either go to the 70 here, follow the line up until we intersect it, and it looks like we're pulling 3 Gs. So you would take 3 times 20, giving us 60 pounds. If you decided to use this chart here, it's 2.923. When you do the math, you can round it to 60 pounds. So it's going to be the closest answer. If a small UAS weighs 12 pounds, what approximate weight would the airplane structure be required to support during a 60-degree bank turn while maintaining altitude? We've got 24, 48, or 64 pounds. Woohoo! I don't think anybody has sent any incorrect answers yet. Either you guys are paying attention or you guys have already taken the course, or both, but thank you for participating. Yes, our answer here is 24 pounds. So during a 60-degree bank turn, again, one of two ways to do it. We've got 60 degrees here, follow that line up until we're intersecting. It looks like we're pulling 2 Gs, or numerically, 60 degrees of bank is a load factor of 2. So we just take 12 pounds, times it by 2, and we've got 24. All right, that was all for today. I'm going to hang out for a little bit if you guys have questions on today's topic. If you have questions on any other topic throughout the course. Next week we have I don't know what topic I'm teaching next week. I'll have to check the calendar. But same time, 5 o'clock Pacific time on Monday. If you guys have questions that come on like later on that you're thinking about, feel free to shoot us an email. Or if you want to put it in the Facebook group, if you're not already part of the Facebook group, it's a great resource, not only for the Part 107 stuff, but it's also nice to be part of a community of other Part 107 pilots or those who are aspiring to be. People talk about tips on growing their drone business, the best models for different things. So definitely recommend joining the Facebook group. I try to hop on there a few times a week to answer questions you guys might have regarding Part 107 side of things. But like I said, shoot us an email or post on there and I'll try to get back to you guys. What is the email address? That is a great question. I'm promoting it and I don't know it off the top of my head. If you go to altitudeuniversity.com, it will be listed on there. Sorry, I don't know it off the top of my head. I will next week. But yeah, so just head to our website, altitudeuniversity.com, and you can find it on there. Thanks for joining me here today.